Hello, welcome back to this video 4-2 on using the first derivative test to help us identify increasing, decreasing functions and relative maxes and mins. Okay, so we're going to go ahead and look at the second example here, and we're asked, okay, where is the function increasing, decreasing, and what are the local extrema? So again, what you have to do first is identify where are domain restrictions. Can you not plug any value in? And in this case, x cannot be 0. That would give us a denominator of 0. It's undefined, so we restrict the domain there. Okay, so now that I've done that, what we want to do is we want to go ahead and identify, okay, what is f prime of x? And I want this to be equal to 0, so we'll solve. Okay, so I need to take the derivative of this. Hey, that is the quotient rule. Boom, there's the quotient rule. Okay, but I want to go ahead, I want to simplify this. So, boom, there, I simplified it. Okay, so after we do some algebraic math, we can go ahead and get this. And then what we want to do is we want to go ahead and factor out our numerator. So our numerator, that really is a difference of two squares. So we have x squared plus 1 times x squared minus 1. And again, all this is over x squared. And what we'll do is we'll factor out that other difference of squares, x minus 1, x plus 1. Okay, and we have our fully simplified version. Okay, good. Now what I want to do, I need to do a couple of things. One, I need to determine what are the critical numbers. Okay, and you can do this two ways. First method, when is this function equal to 0? Okay, so when do I get 0, my function equal to 0? Well, when I have x squared plus 1 equal to 0. Or when I have x minus 1 is equal to 0, or when I have x plus 1 is equal to 0. Okay, so I just took each piece of the numerator, right? I set it equal to 0, and I solved. So again, this will produce imaginary zeros here, so so we don't have any zeros there. Okay, we just keep it real. We're the realist. Here, x equals 1, x equals negative 1. Okay, and then this is, right, for zeros. And then we can also find out, okay, where is f prime of x undefined? And if we look again, our denominator, we are undefined at 0. However, what do we say a restriction value was? Domain cannot be 0. So therefore, okay, I know that x, right, cannot be 0. It's undefined there, okay? So that normally would be a critical value, but since it's removed from our domain, we don't include it. Okay, now that I have all this wonderful information, what do we do with it? Well, we need to make a number line. So I'm going to go over here, just make it a 9. Here is my values. So negative 1, I have 0, and I have 1. Well, what do we say is happening at 0? It's restricted from our domain. That is a vertical asymptote, so I'm just going to draw a line like that. And I have my other two critical numbers. Okay, now what I'm going to do is I'm going to plug in values. I'm going to plug in numbers such as negative 2, maybe negative 1/2, positive 1/2, and maybe 2. And I just want to know what is the sign. So I look at my simplified form of my derivative, okay, f prime of x, and I plug in these values. So I plug in negative 2 here. This gives me a positive. Plug in negative 2. That will give me a negative. And if I plug in negative 2 here, I get a negative all over a positive. So that is a positive, right? Positive times negative, that's positive. Over positive is positive. Okay, next I'm going to go ahead and I'm going to check, and I want to plug in negative 1/2. So if I plug in negative 1/2, that becomes positive, right? That's a quarter, positive quarter. Then I plug in negative 1/2 here. That is going to be negative. And if I plug in negative 1/2 here, that is positive. Okay, the denominator is always going to be positive, so this is negative. Okay, now we're going to do the same thing. I'm going to plug in positive 1/2. So this is positive. This is still negative, and this is positive. Okay, and then the denominator is always positive, so this is still negative. Okay, and then we'll do the same thing with 2. Plug in positive 2. So this is going to be positive. 2 take away 1, that's positive. And then 2 plus 1 is positive over positive, so this is positive. Okay, what does this tell us? Well, it tells us that our function is increasing, and then it's decreasing. Then we have an asymptote. Okay, it's still decreasing here, and then it's increasing. Okay, well, we can go ahead and answer the question now. We can say that the function is increasing on negative infinity to negative 1, union 1 to infinity. Okay, where is it decreasing? Well, it is decreasing on negative 1 to 0. We have an asymptote, right? Then from 0 to positive 1. Okay, so there's the increasing, decreasing. Reading the sign chart. Next, I want to go ahead and find out, okay, where are the relative extrema? Well, my function, if I change from positive to negative, this creates a max. Okay, so I know that there is a maximum, okay, and that occurs at negative 1, and then I need the output. So when I plug in negative 1 into my function, okay, so we'll go up here, f of x, and we'll analyze, okay, what is f of negative 1? And if I plug it in, f of negative 1. If I plug that in, we should get, that'd be positive 1, that's negative 4/3. Okay, so come down here, that's at negative 4/3. Okay, and then a minimum. Well, my minimum occurs at 1 when I change from negative to positive. So min at 1 comma, and then we're going to plug in 1 into our function, and we should get positive 4/3. Okay, so f of 1 equals positive 4/3. All right. So there you have it. There's that example. Okay. Next example. I'm going to go ahead. I'm going to duplicate this page, and I'll do example 3. Okay, and here is number 3. So for number 3, this is a polynomial function, which means that the function is continuous everywhere. So from negative infinity to positive infinity. I don't have any values to worry about that are undefined. Okay, so to find the critical values, I want to go ahead and take the derivative, which gives us 3x squared minus 6x plus 3. Okay, and what we can do is go ahead and now I want to set this equal to 0, so I'll factor this to give us x squared minus 2x plus 1, which is just 3 times x minus 1 times x minus 1. Okay, so we have 3 times x minus 1 squared. Okay, so where does this equal 0? Okay, so what we get is we get multiplicity at this factor, right? And we get a critical number of 1, just 1, that's it. I thought this was supposed to be the most complicated example. Not always. Okay, so I'm going to go ahead, I'm going to make a number line. I have a critical number at 1, and I'm going to test a couple of values. I'm going to plug in 0. Now, if I plug in 0 here, okay, I get a negative 1, which is positive, negative 1 squared, which is positive, so that's positive. And then if I plug in 2, so 2 minus 1 is 1, 1 squared, that's positive. So wait, the function is always increasing. Yes, so this is a monotonic function. Okay, and pretty much what that means is it means that this function is always increasing or always decreasing for all values. Okay, so increasing on negative infinity to positive infinity. So a few notes about strictly monotonic functions. It's, again, increasing or decreasing always, okay? And there's two critical points. Sorry, important points. I don't want to confuse syntax. Not every critical number produces a relative max or a minimum. So since it was always positive, okay, there's no critical value there. All right, even though the slope at x equals 1 is 0, the function is always increasing. And we've kind of talked about these in class before. All right, so in this video, we use the first derivative test to identify critical numbers, and then from there, we plugged in values to do sign analysis to see, okay, is our function increasing or is it decreasing? Catch you next time. Peace.